Good morning, Chairperson, sir. Ladies and gentlemen. Today, everywhere we look around, there is a talk of AI and machine learning and predictive modeling. While we are a long way off from replacing the human, yet decision assist tools are getting smarter every day. I will present the development of one such tool in an area in which it hasn't been attempted before. We know everyone has had a back problem sometime or the other. Military flying has the additional occupational hazard of the flying environment itself, and we see spinal disabilities forming a fair chunk of disabilities in aircrew. The Institute of Aerospace Medicine at Bangalore is the only place in the Indian Air Force mandated to evaluate spinal disability cases of pilots. When we were analyzing our workload data, we found that of all spinal disability cases that landed up in the department, 57% were upgraded to a flying category and 43% were continued in the ground medical category. But this set us thinking that can we predict which pilot would be fit and which one unfit? We didn't buy a crystal ball, but we put on our thinking hats. We studied the data of 120 aircrew who came to us with spinal disabilities. We had to exclude anyone who had other comorbidities. As you can see, when he came to IAM, he had some 11 parameters which were either demographic in nature or had already happened, so were non-modifiable. And there were three parameters which were unique to each visit to IM. The opinion of the concerned clinical specialist, how the pilot perceived his physical status to be. This is what the SF36 questionnaire does. And finally, the functional evaluation that was carried out as per a set protocol at IM. Based on all these 14 factors, the aerospace medicine specialist deemed him fit or unfit to fly. So we now are looking at the ingredients of the crystal ball. The aim was to construct a model of spinal disability assessment in pilots so that it can reflect the final recommendation of the aerospace medicine specialist. There were two paths before us to model this complex decision making process. One was the more familiar path of multivariate analysis and multiple regression equations, but we hit a real world problem. In every case that comes to us, the data on all the 14 parameters may not be available. While in real life, the doctor still gives his opinion that traditional multiple regression models would fail in the face of absent data. But a Bayesian approach would still work. So here's the shortest class on Bayesian modeling. We have a prior probability of an event occurring. In the background of this knowledge, new information is received. Bayes' theorem basically helps us to incorporate this new info into our existing belief, and our prior probability is now revised or updated into a posterior probability. Jargon is always made easy with an example. In the morning, while having your coffee, you read about 1,000 new cases of COVID in your city. So you now have a prior probability or a belief that there is corona around. Now, then, that day in your OPD walks in a patient who has cough and cold since yesterday. This is new info, and this you incorporate into your belief, and even before you do a RAT or an RT-PCR, you have started isolating him. 2 hours later, if another new info comes regarding the test report, again we update our belief. That is exactly what is Bayesian thinking. Rest is just math. In our case, we have a data set which tells us about the prior probability of flying fitness or unfitness by the time a pilot walks into IM based on some factors. This probability is 57% getting flying and 43% not. When a particular pilot comes, his data on each of the following parameters is new info. With each piece of information, we update our belief and finally reach a posterior probability or what we call a prediction. Okay, the actual thing isn't all that simple. But then we have amazing software available to us to help us make the Bayesian model. This particular one has a good user manual and the academic license is free. So we put all the data of the 14 parameters of these 120 pilots into the software and set out to make our mathematical model. The first thing is that we got the structure of the model in place. How do these factors influence each other and interact with each other? A table like this never makes much sense, but the same thing is more comprehensible graphically. So this is how the model structure looks. This is still the bare bones of it. What influences what, which ones directly influence the AVMED opinion, and which ones have a somewhat indirect effect. With this network in place, we then go on to calculate our conditional probabilities for each of these factors. For example, whether he was operated or not. Both are conditions that have their influence on the final probabilities. Again, a graph would make more sense. So this is the final Bayesian belief network, which has the conditional probabilities and the linkages of all the 14 factors that led to the decision flying fit or unfit. If you can make out 57% flying fit and 43% grounded, that's what we started with. We have our model ready. How do we apply it? So a case study, a 30 to 40-year-old pilot from the fighter stream walks in with who had low backache with no new history of trauma. Neurologically, the MRI seems fine and he was not operated. He's done well on the human imaging evaluation. That pilot, when we put it into the model, has got a 95% probability of being considered fit to fly. How do we validate all this? As the first step, we use the leave one out method. We fed in the data of 119 pilots to make the prior distribution. We then tested the model on the remaining one pilot's data, and we did this 120 times. The confusion matrix showed us great results. It did prove that the model or the structure was extremely robust. The predictions were correct 116 out of 120 iterations. And so we decided to increase the degree of difficulty with a particular aim in mind. We took the complete data of 29 different pilots who were not part of the original database of 120. From this, we took 11 parameters which are already present before he reported to IM. We skipped the three data of the clinician's opinion, the subjective score, and the human engineering evaluation. And we ran the partial data in the model. The predictions were correct regarding flying fitness or unfitness in 25 out of 29 cases. It did way better in correctly predicting the flying fit cases. In the flying unfit cases, it correctly predicted 9 out of 12 times. But remember, we had not given it three very important information. Frankly, we were a bit spooked with the results. So how do we use it? It works reasonably well with 11 parameters. It can be used as a decision assist tool at the squadron level. Should I send this pilot to IAM? Is he likely to be upgraded? Does he need more observation period on ground? It's really useful because even if it goes wrong, then it errs on the side of caution. A few pilots go to IAM to be upgraded, but they don't. So it's okay. The next important feature is that every new aircrew can be added to the database and it gets incorporated into the model. So it is constantly learning from more data. And suppose a new modality of treatment came in or there was a change in medical policy, that too can be incorporated into the model. The version is available to anyone with a Windows computer and the academic version of the Genie modeler. But then updated versions will basically need to be given every 1 year or so with more data. On the other hand, it is possible to make a server-based solution for this and make it available on the AFNet. I had said in the beginning that this model includes cases of spinal disability only. We did not incorporate cases who had other comorbidities. But we now feel that another project does need to be taken up to incorporate these parameters as well. To conclude, the Bayesian networks have never been used to predict fitness after spinal disabilities in pilots. This particular model needs further field evaluation and wider implementation. And finally, we in the armed forces are sitting on tons of well-documented data. We do need to catch up on predictive modeling. Thank you, ladies and gentlemen, for a patient hearing.